What's going on, everybody? Welcome again to the channel. Man, we're gonna run through a lot of stuff today. Got exciting, super good news. And so let's get to all this. And yeah, as always, guys, if you like the content, hit the like button, subscribe to the channel, and the bell notification. You can click on that as well, so you can get the these videos, you could get them at a timely manner. So let's go right away. The fear and greed index 45. We got Bitcoin for some reason running, but who knows? Maybe this will drop again. I mean, it's on a swing. It goes 61, drops to 58, goes up to 60, it goes down to 59, and no. But I mean, hey, that's fine. Go up. So we got a few things going up here. Very little. And of course, we got Tron here. Oh, actually turned red when I was looking at it earlier. It's looking like Cardano might flip Tron again. I don't know. We'll see. Exciting times. Apparently there's a lot of things going on with Cardano, but yeah. So don't know. Have not looked into it. Okay, so looking at all our things here, just kind of interested. If we look at the last 7 days, I mean, there's hardly anything in double-digit gains except for Pepe coin. Okay, and so still doing pretty decent. Last 24 hours, $2.16. So it's been a bit of an uptrend. Okay, this is good because there's some good news coming out of the Pepecoin and Base AI team. Giga Chad has been slowing down. Sundog, my goodness, this thing was at $200 million like what, 30 minutes, an hour ago? And while I was doing my research, and now it's just great, guys. That's why I stopped chasing these things. Look at Nero, another one too. Look at this, 28% in the red. You guys remember Michi? Yeah, look at where Michi is at. Look at this, all the way down to $62 million. Can it go up? Absolutely, it could go up. I'm just telling you, it's these things are just people pump it and other people follow it, and then they notice, oh, smoke, like this thing has absolutely no use, no nothing. It's just a picture of your cute cat. A lot of people are gonna have to learn the hard way, but that's not the case for Pepe Coin and Base AI, guys. So let's get to the news. Deving our way to the top. Nobody's ready. Boom, guys, this is amazing. This is us right here. Okay, just absolutely cool as a cucumber. Why is this not working? Anyways, cool as a cucumber, just walking up. Things are happening all around. Everything is just falling apart, and we are comfortably going up. Yeah, but this is the big news, guys, and it is that as the Base AI Cyan testnet ends in preparation for the brain burn, Base AI will be conducting a final test of the network's ability to mirror Ethereum for complex multi-owner brain updates. Follow along on the Base AI test Ethereum mainnet address. Follow other changes on the Base AI by running. Okay, so you got this. So oh, cool. Yeah, so I wouldn't mention this. So apparently Cyan network is soon going to be coming to an end, which is exciting. At the same time, it's kind of like sad because there's a whole bunch of us that have been mining quite a decent amount of base tokens, and so but that's fine. We'll continue to mine that with our Pepe coin as well. We could still do it with our base AI tokens, But yeah, but hey, it's okay. This is what we want, right? Because that means that soon enough, the burn, guys, the burn is on its way, is coming soon. This is excellent, 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 excellent news. So, yeah, so they're just going to be conducting some final things, right, on the network. They just want to double, triple, quadruple check that, things, nothing breaks. And even when things go live, expect things to break and, you just, because that's just part of the whole, process. And so somebody asked here how we will migrate our base AI tokens. So they're going to have a one-click bridge and claim to get mainnet base. So it's gonna be extremely easy to do so. Pretty cool. Super exciting. And we've been on our little journey over here, which we're gonna continue today. I kind of got freaked out when I saw news. I was like, oh my goodness, we have. But I mean, at this point, if this project is not for you, by now you've probably figured out base AI is not for you. Or by now you probably figure out, oh man, like this thing has way too much to offer. And you yourself decide to pull, whatever it is that you're gonna end up doing, if you want to invest or whatnot. Because none of this is financial advice, guys. So, okay, so the governance and Gigabread. We're gonna try to get through this as fast as possible. So Peppercoin is an ERC20 token, right? And it's used within the base AI network for distributing brains, which are crucial elements in the system, right? So we know that this is when we burn the Peppercoin, or when you stake 100,000 Peppercoins to get a brain. These brains are going to be, as we have mentioned before, NFTs, right? So non-fungible tokens on Ethereum, okay? So they're going to be ERC 721 standards. When a brain accumulates 0.5% or more of the total network stake, it is upgraded to a gigabrain. Gigabrains have the power to vote on important network decisions, with each gigabrain having one vote. Even if a brain's stake continues to grow beyond 0.5%, it still only gets one vote per gigabrain. Okay? However, users can own multiple gigabrains, each with its voting power. Additionally, Peppercoin holders are also allowed to participate in the governance of the network, giving them a say in how the base AI network operates. So if you have Peppercoin, you don't get to vote, but you still get to participate. And so here is the schematics, right? You have Peppercoin, you burn Peppercoin, or you stake the 100,000, you get a brain, okay? Your brain gets that 0.5% of stake. Now you become a gigabrains, okay? And now this gigabrain gets this voting right, and they propose, exert, so they get to exert, okay, gigabrain voting process, and they propose, to the base lab leadership, okay? The same thing here. Peppercoin influences, okay, the base lab leadership, and the base lab leadership oversees, okay, the network governance, but the gigabrain voting process is what influences what happens here. So hopefully this makes sense. In the first year after the creation of the Genesis block in the base AI network, the leadership at Base Labs will have significant influence over network governance. During this period, any proposals made will automatically pass unless they are explicitly rejected by a majority vote. This governance structure ensures that the network can evolve quickly under the guidance of the leadership team. Additionally, brains within the network will undergo a basic security audit. This process requires brain owners to share links to their Git repositories, allowing miners and validators to review the code associated with brain tasks. This practice provides an additional layer of trust and security within the network, helping to ensure that the tasks run by brains are reliable and safe. Okay, so pretty cool. So we just finished this 3.6. So now we're going to go to section 4, Cerberus Squeezing and model optimization. Okay. So this is the normal unencrypted model. Okay. So you have a user sends data. The data goes to the server sends it to the model. Okay, that's going to, decipher this code. And so once this deciphers the code, you got the message. The message goes to the server, and then the server sends the result to the user. Boom. So the LLMs, particularly those from the GPT series, have contributed substantially to the progress of AI. So ChatGPT and the such, right? Yet the commonly employed architecture for public-facing LLMs, as depicted in Figure 2, where is Figure 2? Oh my goodness. Okay, never mind. It's somewhere up there. Inherently presents several privacy risks. These include, I think this is actually talking about this figure here. These include, but are not limited to, potential vulnerabilities for encrypted data transfer, compromised servers, and the unauthorized surveillance of model interactions and outputs, which is true. So integrating FHE into large language models significantly enhances privacy by allowing computation to be performed directly on encrypted data. This means sensitive information can be processed without being decrypted, maintaining confidentiality throughout the entire process. FHE is a powerful cryptographic tool because it supports operations of encrypted data, which traditional encryption methods do not. However, so you have good stuff. Now let's talk about the bad stuff. So there's some bad news with FHE. So FHE comes with substantial trade-offs. Unlike regular encryption, which can encrypt and decrypt data in bulk, FHE operates on encrypted data bit by bit. So very little pieces of information are being encrypted, right, at the same time in the FHE. In the regular encryption, just take a whole bunch of information, you just encrypt it. So FHE operates on encrypted data bit by bit. Each mathematical operation, no matter how simple, requires complex transformations. These transformations often involve polynomials or integer arithmetic under encryption, significantly increasing the computational load. So FHE actually adds more workload because it encrypts smaller pieces of information. Okay? Additionally, FHE introduces noise with every operation. This noise must be managed carefully to avoid errors in decryption. The more operations performed, the more noise accumulates, which requires further adjustments to keep the data secure and the operations accurate. In practical terms, this means that even basic arithmetic operations become computationally expensive, leading to longer processing times, higher energy consumption, and the need for more powerful hardware. So, I mean, when it comes to FHE in the security aspect, the best. But when it comes to the money, right, it's money and time. It takes longer time to decrypt, and it takes more money, right? Because it requires more time and more, more powerful computing. So here in this example, right, with the FHE, so the data is encrypted. It is sent over the server sends it to the FHE model. The FHE model goes ahead and decrypts this thing, and it just boom, blah, 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 and then this here information is sent to the server, and then the server boom sends the information to the user. Okay, and so the user must have some key or something so you can decrypt this message. Okay, so and so let's say, for example, right in here, this a plus b plus c times e and all that says, for instance, a simple expression like a plus b plus c times d plus e times f would typically require only one encryption step in traditional method, right? Because it just bulks it. It'll just take everything. However, with FHE, each variable and operation needs to be encrypted and computed individually, multiplying the computational requirements. This results in significant performance trade-offs, making FHE for LLMs more resource intensive compared to unencrypted and traditional encrypted computations. Again, what we were saying, it's just kind of repeating itself here, right? It's just, it's gonna take longer for the FHE to solve this, right? Or to encrypt this and decrypt it than if you were to just do the traditional method, which would just bulk it out. And so here it just says, conversely, the FHE process necessitates that each bit is encrypted. In this simplified example, that means each variable needs to be encrypted. So 1, 2, 3, 4, 5, 6. And each function needs to be encrypted. 5. I don't know. What is the 5? 1, 2, 3, 4, 5. So I guess each function, right? So 1, 2, 3, 4, 5. So you have a total of 11. Okay. So if it was a traditional encryption, it would just be 1. If it was FHE, this thing would require 11 variables, right, are gonna need to be encrypted. Okay, so, and here we are, right? 11 for FHE. So it's the computational steps that you need to take. And for the standard encryption is just 1. So obviously this is going to be super fast and very cheap compared to FHE. But then here, to optimize this FHE performance, now they're going to introduce Cerberus Squeezing. And so this technique, okay, is to mitigate the heavy computational demands typically associated with FHE. So because FHE takes so much power and so much time, now we're introducing this Cerberus Squeezing to help that process. This technique applies deep compression principles. So it's kind of like a method used in model quantization to reduce the operational load while maintaining the privacy benefits of FHE. Cerberus Squeezing specifically targets selected layers within the LLM architecture, optimizing the encryption and computational processes by restructuring how data and arithmetic operations are handled. For example, if an unoptimized FHE setup, each element and operation in a calculation would require individual encryption and computation, right? We just established that. So every single variable is going to require an individual encryption and computation, leading to significant overhead. However, Cerberus Squeezing merges these operations, compresses multiple arithmetic tasks into fewer, more efficient encrypted computations. So using the simplified arithmetic, right? So here the AB, this one. Traditional FHE will require 11 distinct encryption actions. By contrast, Cerberus Squeezing reduces this to just 5. Okay. actions by enabling certain operations to be performed collectively in a single encrypted step. This is not only lower, this doesn't only lower computational costs, but also ensures that data remains encrypted throughout, safeguarding privacy without compromising efficiency. Through such targeted targeted optimization, base AI aims to make the deployment of privacy-preserving LLMs feasible in decentralized networks, enabling secure and efficient AI ML operation at scale. So here we're going to see this other graph. So this is FHE, right? So we know that the standard is 1 and FHE is 11. But FHE with this Cerberus squeezing is going to be, it's going to cut this more than half, okay? So it would be 5 steps rather than 11, which is quite significant, honestly. The integration of Cerberus squeezing into base AI framework, particularly for ZK LLMs, represents a significant advancement in privacy-preserving machine learning. This method focuses on optimizing the multi-head attention (MHA) mechanism, a critical component in transformer models like GPT-2 and its successors. The MHA mechanism in transformers is highly computational, making it a prime target for efficiency improvement when paired with FHE. So this whole multi-head attention mechanism here, this is what the Cerberus squeezing is, it's working on to try to make the FHE, a technology that could be feasible, to use. Cerberus squeezing adapts the forward pass of these models to manage FHE operations, what we're just talking about, while maintaining the encrypted state of the data. You see, the whole thing is you want the information to remain encrypted, secure throughout the entire process, no matter what the cost, right? But you also want to be cognizant of that, right? And so what the team has done is, okay, so we want to maintain this super sensitive information. We want to maintain it as private as possible. And so to make that, still a better option to use, then of course there comes the Cerberus squeezing that goes ahead and, it's able to bring down these steps to less than half of what it would have been. This ensures that sensitive information remains secure throughout processing, even with a decentralized network where multiple participants may interact with the model. By refining how the MHA operates under FHE, base AI allows for the efficient deployment of these models within a computational budget, critical for large-scale decentralized network, which is very true. Moreover, because the Cerberus squeezing technique is designed around the MHA mechanism, it is compatible with any transformer-based model. This includes current models like Llama, LLA-MA, and future models like GPT-5. Consequently, any transformer model can be integrated into the base. Boom. Whoa. You guys hear that? Consequently, any transformer model can be integrated into the base AI network and transform into a ZK LLM, allowing it to operate securely without sacrificing privacy. The key benefit of Cerberus squeezing is that it bridges the gap between the high computational cost of FHE and the need for efficient, large-scale AI operations, making privacy-preserving AI a practical reality in decentralized network. And that was exactly what I was saying, right? It's just to be able to have this technology, right? Have this privacy, and and the way to be able to do that is by being competitive, right? And so you don't want to be the most expensive thing out there, but of course, it's the best privacy, the best security. But at the end of the day, I mean, if it's too expensive or too time consuming, it's a practical, and you want to make it practical, right? And so Cerberus squeezing is what gives FHE the ability to actually compete in the space. Hope all that makes sense. To improve the performance of FHE, the core of the Cerberus Squeezing is optimized when the brain routes the task for processing to the miners. By default, the embedding are stored in the miner and on the nodes of the brain's distributed work. So imagine, okay, so let me see. Yeah. So FHE, right, again, it's super complicated, so it can slow down the computer work a lot. So to try to fix this, base AI uses, right, the Cerberus Squeezing. Right, this is like squishing together some steps, so your computer, can do it faster. And so that's pretty much what it is, right? Optimizing Cerberus Squeezing, right? It's just making it better for, making it better so that it can, process the information as fast as possible. By sorting embeddings at the miner level, the network can significantly reduce the computational overhead typically associated with FHE operations. So this kind of like, so this step, right, of sorting, okay, so it's more doable because it can actually kind of like send it to miners, okay? And because it can do that, then the network can reduce its computational overhead, okay, which could be completely bogged down by the FHE. This is achieved by optimizing the manner in which encrypted data is handled, ensuring that each node processes only a relevant portion of the task, minimizing redundancy and improving process speed. This distributed approach allows the brain to effectively manage computational tasks, ensuring that encrypted operations are executed efficiently across the network. The Cerberus Squeezing technique further streamlines this process by applying deep compression principles, allowing FHE tasks to be performed without compromising security or efficiency. The result is a more scalable and responsive system capable of handling the complexities of ZK LLMs within the decentralized environment of base AI. And that's practically it, guys. I mean, so today we spoke about Cerberus Squeezing, right? We talked about the governance, okay? So what roles Peppercoin holders are gonna have, what roles Brain holders are gonna have, what this GigaBrain title means once you hit that 0.5, right, percent of the total stake of the network, you become a GigaBrain, and then that gives you governance power to make changes and stuff like that. And then we saw, right, the schematic here, and then we saw the Cerberus Squeezing. So hopefully this was completely, simple. FHE, very, very secure, but a lot of steps, a lot of computing power, and a lot of time, which all equals to a lot of money. Cerberus Squeezing comes into play, and it helps it helps cut down all the steps, okay, that the FHE is producing, so that it can be practical, okay, out in the world, and so that people can actually use it. Okay. Now, I read somewhere, I think it was in, was it here? Let me see. let's see, Pepe Corners. And I think, okay, yeah, here. And so did a summary of the entire conversation between the community and the devs on the Telegram. There's a huge conversation which includes a great deal of new information about how its mainnet functions, the schedule ahead, and the intention behind the tech. Okay, so they did all this. Oh man, I don't think it was here. But anyways, there was, I don't know, maybe I was in the Telegram myself, and they were saying something that they were going to update the white paper. Okay, not, I don't know what that means. I don't know what part of the white paper is going to be updated, but hopefully we get that information sooner than later, as we are going through this, you know, point by point here, step by step, section by section. So when that happens, you know, hopefully if there was something that we already covered and maybe they changed, we can go back and, you know, quickly touch up on those points, and hopefully, you know, I'm pretty sure it's probably going to be better changes than not. So guys, again, thank you for your attention, for the support, for the subscribing, for the just being here, man, and just learning. It probably means that you're a geek like me. I do find this pretty interesting. Not that I'm a tech at all, like absolutely not. I'm no techie, but this is really fascinating, and ChatGPT does help a lot. You know, you guys could do the same thing, but I know that most of us don't have time, and so, you know, that's my case, is that I do work a 9 to 5, and I get out of work, or a 4 to 1. Today I worked almost 4 to 2, 4 a.m. to almost 2 p.m. And you know, and I got home, walked the dog, feed the dog, and, you know, try to do some things around the house. In the meantime, try to do some research and try to bring you guys, you know, some relevant information. So I just sure hope that you guys appreciate this, and if you do, just give me a subscribe and a like. Just help the algorithm. You know, that's all. Hey guys, y'all have a blessed day, and I'll see you in the next video. Take care. Bye bye.